So Preet, I'll make you a host again.
Great. Do we start?
Yes, we can start this.
Okay, I think it's already 9 o'clock. Maybe I just start the session.
Yeah, please go ahead.
Okay. Hi. Good morning, everyone. Welcome to Tuesday session, morning session. My name is Wang Xiao. You can call me Renshou. I'm the chair of the morning session. This morning session, we have 3 talks. The first talk will be given by Prof. Kondo. And the talk is about a study on neuromorphic computing-based path planning and moving object avoidance. Prof. Kondo, is everything ready on your side?
Good. Can you see my screen?
Yes, I can see your screen.
Okay.
Great. Talk will be 40 minutes, including Q&A, I believe. So now the stage is yours, and please welcome.
Okay. Good. So first of all, thank you very much for inviting me to this great seminar. And my talk is about a study on neuromorphic computing-based path planning and moving obstacle avoidance. Sorry, I'm Masaki Kondo, and Faculty of Science and Technology of Keio University. Okay, this is the content of this talk. I'm going to first talk about briefly the background of this talk, and then I briefly introduce basics of spiking neural networks. Maybe you already know details of spiking neural networks, therefore I will make this quick. And then we briefly talk about the path planning approach with spiking neural network. Then we propose agent-based path planning approach. And then finally, I will show several simulation evaluation for this proposal. Okay, then the first is background. Okay, so my research background is actually computer architecture. Especially we are working for important research challenges of end of Moore's law. As you know, it is expected that the CMOS scaling trend will end in near future. So we have to tackle this problem. This is a very famous chart showing microprocessor technological trend over the past 40 years. For example, clock frequency improvement showing green line stopped at the middle of the year 2020. So this is mostly due to the power consumption. Because we cannot provision power onto a single chip due to the limitation of cooling capability of a single chip, we cannot increase clock frequencies so that the power consumption of the microprocessor is almost stable over last maybe 15 years. Therefore, we can observe only a moderate speed up of single thread performance shown in the blue line. But one of the good news is that still a number of transistors integrated in single chip showing this orange line increases. So we can improve our performance by increasing number of logical compute cores. However, it is said that the scaling trend of this transistor count will end in next 10 years. Therefore, in near future, we won't have any speed benefit, no more power reduction, and no more transistor on a single chip with CMOS scaling. So we need to explore next generation computing paradigms for coming post-neural era. There are several potential solutions, including non-von-Neumann architecture, quantum computing, and then neuromorphic computing. And we are seeking for how neuromorphic computing is beneficial as next generation computing paradigm. So in this talk, I'm focusing about path planning applications. Path planning is a kind of very old and very famous and conventional problem, which tries to find an appropriate path from the start position toward the goal, usually on a graph data structure like here. There are a lot of application areas that requires an efficient path planning algorithm, such as autonomous mobile robots, navigation services, and self-driving cars. There have been proposed many techniques to solve path planning so far. However, there are still several challenges to be addressed. For example, the algorithm requires high compute efficiency for realistic problems, especially for mobile devices. Also, they need to have capability of handling dynamic environmental changes. Since the real-world environment is actually dynamic rather than static, this handling dynamic environment change is very important. And in this talk, we introduce a method for path planning based on neuromorphic computing to tackle both challenges. But this talk does not propose any hardware aspect of neuromorphic computing, but just introduces an application of neuromorphic computing. Therefore, our method will benefit from any efficient neuromorphic hardware designs, or more specifically hardware for spiking neural networks, introducing maybe several other talks in this seminar. So of course, most of the audience of this seminar are very familiar with neuromorphic computing. Therefore, I wouldn't need to say much about it. Therefore, I'm going to say only a few words about the background of neuromorphic computing. There have been numerous efforts about neuromorphic computing research, especially for achieving high compute efficiency. Neuromorphic computing is, of course, a computational paradigm which imitates neurobiological architecture in nervous system, and it is known to be applicable to shortest path finding problem. And recently, this paper shows them how to solve the shortest path finding problem by spiking neural network. Because spiking neural network has an inherently parallel processing nature, so that the neuromorphic hardware can solve the shortest path finding problem with high speed and low power consumption. That is the main motivation of using neuromorphic computing for the path planning problem. So our target problem is path finding on a graph, where we would like to find an appropriate path from the start node, shown here, and to the goal node, shown here. We assume that there are several obstacles in the graph, showing maybe a purple circle. We cannot go through the node or edges where obstacles are located. Important point here is that the obstacles move by themselves. Of course, in real world situation, for example, assuming self-driving cars, the obstacles may be the other cars or maybe humans around the car. And of course, they move by their own purpose. So we need to avoid the collision to these obstacles. Also in this figure, we assume there are several moving obstacles in the graph, and we need to find the path avoiding the collision to these moving obstacles. Okay, so let's move on to basics of spiking neural networks. As you may know, spiking neural network, or SNN for short, is one of the ways to realize neuromorphic computing. In an SNN, the neurons communicate with each other with a simple spike-based signal. The SNN is also a kind of mathematical model to reproduce an activity in cranial nervous system. But compared to artificial neural networks, the behavior is more close to the cranial nervous system. Roughly speaking, the spike neural network is characterized by Neuron Model and the Synapse model, as well as the weight, which are commonly used in artificial neural networks. In this figure, this shows an elementary component of spiking neural network, of course, neuron and synapse. A neuron is characterized by several parameters like membrane potential, threshold potential, and also peak and reset potential. And synapse is characterized by signal transfer function shown in function f over t. And also it may be characterized by delay. And also this elementary component is connected together to form a neural network. And the edges between the neurons has an parameter of weight. By mapping the problem of shortest path finding problem on spiking neural network, and also by designing these parameters properly, we can solve the path planning problem by this spiking neural network. So in this research, we assume to use a very basic neuron model, that is leaky, integrate, and fire neuron model. In this model, input current is integrated in the membrane potential of the neuron, and the potential, or say electric charge in the neuron, peaks over time. And the figure shows spikes coming from adjacent neuron to the target neuron, showing there are 5 spikes over time. And the bottom here shows membrane potential of this neuron. When an adjacent neuron fires and emits spike signals to the neuron, the membrane potential of the neuron increases. And when it reaches a predefined threshold, it will fire. And then it's suddenly the membrane potential drops to the reset potential. Since there is a leakage term in the neuron model, the membrane potential gradually decreases if no spike signal is input to the neuron, for example, in this duration. Okay, let me explain the path planning approach with spiking neural networks. First, I'd like to talk about how to solve the pathfinding problem with spiking neural networks, without having moving obstacles. We can solve shortest pathfinding problem by 3 steps shown here. The first step is the mapping of the target graph onto a spiking neural network. So each node of the graph is assigned to a neuron of spiking neural network, and each edge of the graph is mapped to the symmetric pair of synapses. Therefore, for a given graph, we can directly map the graph to the spiking neural network. For our purpose, we especially use a self-loop synapse model, which connects a neuron with itself, as shown in the yellow arrow. And this is used to make a fired neuron continuously fires. Okay, the second step is the forward search to derive the required time to reach the goal node from the start node. We first stimulate the start neuron shown here. And we stimulate this neuron at time t equals 0 and make it fire. And of course, the spike pass through the connected synapses, and adjacent neuron also fires once the membrane potential exceeds its threshold. In this movie, neurons which haven't fired yet are shown in blue circle, and fired neurons are shown in yellow circle. And having several time steps, eventually goal neurons here fires at time t. The time t indicates the shortest time to reach the goal. In this example graph, we can see that the goal neuron fires time equals maybe 5. Okay. Finally, we derive the shortest path by performing the backward search, which indicates that we search the path from the goal node to the start node. Before we activate this spiking neural network, we inhibit neurons which did not fire in the forward search in each time step in the backward search. Then we estimate the goal neuron. We stimulate the goal neuron and keep track the fire neuron path until start neuron fires. And this red node indicates intentionally inhibit neurons. So by tracking the firing neuron showing yellow, we got the shortest path in this example, like this path and showing here. This is shortest path in this graph. Okay, so we now propose the agent-based path planning approach. So when obstacles do not move, or when their movement is known in advance, we can derive path to the goal at the beginning. I mean, before the target agent starts to move. However, usually obstacles movement is unknown in advance, and therefore the shortest path to the goal cannot be determined at the very beginning or at the start time or t equals 0. To deal with such a dynamic changing graph, we introduce a concept of the agent, which determines next node to go every time step. Therefore, we have several steps, and each time step we perform the same algorithm as I described previous slide. In our research, we compared 3 agents. The first one is the greedy agent with the traditional simple greedy approach. And then we proposed the other 2 agents called the neuron threshold-based agent and synapse efficiency-based agent. I'm going to explain these 3 agents in the following slide. The first one is a greedy agent. The greedy agent always tries to obtain the shortest path, considering only the present position of the obstacles. So in this figure, this rectangle shows the agent, and this is the goal, and the purple ones are the obstacles. At the start position in this figure, the agent calculates the shortest path, and maybe it moves to its bottom right diagonally, since this is considered as the shortest way to the goal in this situation. After that, suppose the obstacles moves like this, and then agent drives the shortest path again. And maybe in this case, the shortest path is expected to be like this path. But the problem of this greedy approach is that it is likely to have collision to obstacles. Since the purpose of the greedy agent is only reaching its destination promptly, and because collision to obstacles should be avoided in the real world situations, we need an appropriate agent algorithm which has 2 purposes: not only reaching its destination promptly, but also in avoiding moving obstacles properly. So the purpose of our agent will select a proper path concerning how to avoid the collision to the moving obstacles. So to avoid collisions to obstacles, one of the ways in the SNN-based algorithm is making neurons corresponding to or near to obstacles hard to fire. That is a key point of this method. So if we first describe neuron threshold-based agent for that purpose. So we make good use of threshold potential of each neuron in this agent. So by increasing the threshold of corresponding neurons, the neurons becomes hard to fire. For example, this here shows membrane potential over time. And in this left figure, if the threshold is 1, and if the input current is applied to the neuron at time 3, the neuron fires at time 4. On the other hand, as on right figure, the threshold becomes 3, and also the input current is applied to time 3. And but the neuron fires at time 6. This means that the neuron becomes hard to fire compared to the other normal neurons. Therefore, for example, assuming these neurons corresponding to the obstacle position, and then we increase the threshold potential for these neurons. As a result, the agent will select the neurons of a small threshold, like this spot, for spiking signal transition. Then it can take a detour, avoiding collision to the obstacles. So our second proposed agent is synapse efficiency-based agent. In this agent, we parameterize synapse efficiency or synaptic weight of each synapse. The bigger the value of synapse efficiency, the more signals the synapse conveys. So we vary synapse efficiency based on the STDP or spike timing dependent plasticity rule. STDP is a biological process which adjusts strength of the synapse connection based on relative timing of coming spike. In this method, obstacles generate special signals, and synapses which frequently encountered signals reduce their efficiency so that neuron that is connected to corresponding synapse is hard to fire. That means the path to the obstacles is hard to be selected in finding the shortest path in the algorithm. So this slide summarizes the operation or procedure of both proposed agents for each time step. And besides stimulating start node in the SNN-based path planning algorithm, we stimulate the neurons corresponding to the obstacles and obtain the firing time. And based on the firing time, we design a set of threshold of each neuron or weight of each synapse, as described in the previous slide. And then we serve the shortest pathfinding problem on the SNN by the basic shortest pathfinding algorithm. After that, the agent moves to the next node according to the obtained path, avoiding moving obstacles. This set of procedure is repeated until the agent reaches the goal. Okay, let me explain the evaluation results, experimental results. So first, I would like to describe an experimental setup we would like to compare the performance of three agents on the three-dimensional grid graph as shown in this figure. The size of the graph is 30 by 50 nodes. And here is the start node, and here is the goal node. The purpose of the agent is to search the proper path from the start node to the goal node, avoiding the collision to the obstacles shown in this purple dot. For demonstration purpose, we assume there are 5 obstacles which can move to a random direction within the movable region. Initial position of obstacles are randomly set. We assume it takes 2 steps in one vertical or horizontal movement and 3 steps in diagonal movement. Each square of grid is mapped to a neuron, and therefore Synapse connect adjacent square in this field. And this slide shows a demonstrative behavior of Synapse efficiency-based agent. The left side figure indicates the state of the current graph. And this light green shows the current position of the agent, while purple dots represent the position of obstacles. The green line is obtained proper path in each time step. And the right side figures indicate the value of Synapse efficiency for each time step. The darker the color of the arrows, the higher the negative efficiency of synapses. As seen from this animation, the agent tried to reach the goal node, avoiding these obstacles. I'm not sure how you feel as this movie, the goodness of the finding path, but I think the agent moves a proper agent find the proper path, avoiding these moving obstacles. Notice that we can obtain the similar behavior in the neuron-based agent. So therefore, we can say that the proposed agent works properly and may be efficient to find the proper path, avoiding moving obstacles. For quantitative analysis, we did another set of simulations. We vary the number of obstacles from 2 to 5 and take 100 trials for each cases for each agent. In each trial, once the agent contacts with an obstacle, we count that trial as failure. And when the agent can reach the goal node without any collision, we count that trial as a success. And then we can calculate the success ratio as well as the number of steps to goal. There is another parameter to be optimized in the proposed agent, which is degree of obstacle avoidance. We can change this parameter based on the target situation where how collision to or getting closer to the obstacle should be avoided. This figure shows an example of obtained paths with changing the parameters for threshold-based agent and Synapse efficiency-based agent. For your left, the figure shows the case of small avoidance, and for your right, the figure shows the case of large avoidance parameter. So if we use a large avoidance parameter, for example, this figure, the obtained path is likely far from the obstacles, which is safer in terms of collision avoidance, but it will take a long time step toward the goal. Therefore, we can control the trade-off between reaching the destination promptly and avoiding maybe obstacles properly. In the numerical evaluation, we also vary this parameter. So here is the result. So this table shows the success per trial ratio of each agent. So we evaluate 4 cases of number of obstacles for a greedy agent, neuron threshold-based agent, and Synapse efficiency-based agent. And for threshold-based and efficiency-based agent, we evaluated 2 cases of the parameter for avoidance. As seen from the table, the threshold-based agent and efficiency-based agent have large successful ratio compared to the greedy agent. Especially, we see the case for 5 obstacles. The threshold agent and efficiency agent keeps a high successful ratio of more than 90%, whereas successful ratio of the grading agent drops to 68%. So in the agent prioritizing evading the obstacles, they can achieve high success ratio. This indicates that parameter of obstacles avoidance works well. And here shows, in this slide, I'm going to discuss how fast the agent reaches the goal. This table shows the average number of steps to reach the goal node. Also, we compared 3 kind of agents with 2 to 5 number of obstacle cases. We also vary the avoidance parameter for our proposed agent. Now, from the table, we see that the average number of steps for the greedy agent does not change very much when we vary a number of obstacles. This is because it does not try to avoid the obstacles. It does not care even the situation it is very adjacent or close to some obstacles. On the other hand, in the proposed agent, the average number of steps increases as the number of obstacles increases. Since they try to make a detour every time they become closer to the obstacles, the average steps increases for a large number of obstacles. Also, it is obvious that we use a large avoidance parameter. They need a more number of steps to the goal. Compared to the greedy agent, the increase in the number of steps for the proposed agent is not very significant. Still comparable to the greedy agent, this indicates that the proposed method can find the proper path solution with the moving obstacles avoidance. Okay, so this is time. So in conclusion, in this talk, I introduced spiking network-based method to find the proper path with existence of moving obstacles and show the effectiveness of agent-based algorithm. And okay, so I'm skip for this description. I hope we can evaluate our techniques on several accelerator hardware for spiking network and see how it's effective in terms of actual time to solution and energy consumption. Okay, that's all. Thanks for your attention.
Okay, great. Thank you very much for the nice talk. I think the session is open for Q&A. We have about 8 minutes for the questions. For the audience, if you have a question, you can just raise your hands or either post your questions in the chat window. Probably I can.
So we have disabled the chat window.
Oh,
I can just unmute and ask question. So maybe I start with the question myself. Professor Kondo, I have a question on the synaptic weight and your circuit weight. If you go to slide 19.
Yeah, sure.
Normally, the materials people, when we make a synapse, we think that the synapse itself stores the weight. But in your definition, you say that the network has weight, but synapse doesn't have weight. Can you explain the difference?
Yeah, I think it can be the same, depending on kind of the implementation. Maybe synaptic weight can be changed. Like I mean, this weight can be controlled by synaptic weight stored in like your hardware.
Okay, so in your case, you are assuming the weight to be independent of synapse.
Independent, but as I said, I guess I dependent on the available hardware or the neuron kind of implementation. I think this way can be implemented in the Synapse itself.
Okay, thank you.
Does that answer your question?
Yeah, okay, thank you.
Prof. Kondo, maybe I can ask a question.
Mm-hmm.
So my understanding is during the path searching, so you are assigned the weight to the synapse. Am I correct?
Sure.
Okay, so basically the weight is the path. So you find the best, whatever the whatever highest or lowest weight, then you will find the optimized path, right?
Sure.
So basically that means kind of following Prof. Prem's question. Sorry. So basically the memory is stored in the synapse. Am I correct?
Say again, please. Memory.
Okay. Is the stored the basic memory?
I'm sorry, I
Result
cannot hear you.
In terms of the weight.
Renshaw, your voice was breaking. Maybe you can repeat your question.
Okay, can you hear me properly?
Yeah, no,
Okay.
it's okay.
Great. So basically, my understanding is the results is stored as the weight in the synapse. Am I correct?
Also, it depends on the like implementation, because in the current research, we use a kind of software-based like simulation. We store the kind of like such an information on separately. But of course, in the real hardware, I think we should that such an information should be stored in Synapse, or maybe store a location close to the Synapse.
I see. But then how about the neuron? Would you like have the sort of the storage function?
I guess for neuron, if we can control for neuron threshold-based agent.
Yeah, the firing.
Once we can control the threshold potential, then so besides that, I think we don't need any storage.
Okay, but the threshold would not serve as kind of memory.
I agree. Yeah, sure. You're right.
I see.
Yeah, exactly.
Okay. Yes. Let's see. If no question, maybe I can ask one more.
Yeah.
Okay. For the network, may I know, in comparison with conventional path searching, how much improvement do we see in the neuromorphic-based path searching?
So it is currently ongoing research. We designed very simple hardware of spiking neural network, and our preliminary result is slightly kind of better. Of course, we haven't optimized this hour circuit yet, but our preliminary result shows that it's still a very high kind of energy efficiency compared to kind of processor software-based approach. But still, that's ongoing research.
I see. But let's see if we the network, if we enlarge it like 100 times or the 1,000 times, do we expect like major, very obvious improvement in terms of the efficiency?
I think yes. I guess so, because for CPU-based or software-based approach, it should have a lot of memory accesses, and of course it has a lot of computations, and should be likely sequentially should be done. But for of course neuromorphic hardware can perform that operation in parallel with very low voltage operation. Therefore, I expect quite kind of low power consumption. Yeah.
I see. Okay. Seems we have one more minute. You did mention the hardware implementation because it's ongoing work. And what you're discussing today looks like more simulation-based results. Sure. I'm curious, how do you implement this? Do you use memoristors or use conventional chips, and they make your own architectures? So how do you generally implement?
It's just a conventional chip, digital signal processing.
Okay. So use the conventional chip. I see.
Of course, if we can collaborate with some like researchers, I'd like to try for evaluating with such a memory chip.
I see.
The best one.
Okay. Great. Okay, I think it's almost perfect in time. And thank you very much for your nice talk. And
Thank you very much.
thanks. The next talk is from Professor Tanaka. Let's see whether Prof. Tanaka is here. Yes. So, Prof. Kondo, you can probably, okay, this is already the screen. We can see the screen correctly. Okay, so the next talk is from Prof. Tanaka. We can see his screen already. And Prof. Tanaka's today's presentation title is Data Storage Consideration in Brain-Inspired Applications. So please, Prof. Tanaka, you can, I think the stage is yours and you can unmute yourself and welcome your presentation.
Thank you for introducing me, and that's great, great opportunity for me to give a presentation here. So my talk will be a data storage consideration in brain-inspired application. It kind of is wide view of the brain, how we can learn from the brains and how we can translate into computation systems in it. Yes, I'm Yoichiro Tanaka from Research Institute of Electrical Communication in Tohoku University. Okay. So, firstly, I'd like to express my appreciation to the support by JSPS granting aid for research, scientific research, and Advanced Institute of Iota Informatics of Tohoku University, and HGST and Kioxia Corporation. And also my collaborators are Yosuke Bando, the synthetic neuroscience team in MIT, and Professor Hirano and Yamamoto and Simon Greaves, Tohoku University, and my students, Yuki Kawada. And I also, thanks to supported by NTU Singapore and JSP Japan, and to joint seminar BICPAMA. Thank you very much. So today, this is the outline. The first, I'd like to show the data in society and the brain. And the second is a brain neural structure analysis. That is ongoing project. And third, compute structure in brain. That is very interesting things I'd like to learn. And the fourth, this is the modularized compute, which data store embedded in it. And finally, I'd like to summarize it. Okay, let's look at the origin of digital data. So we live with digital data society, and the digit 1 and 0 is too much simple. It's very simple. And originally, the binary number system was invented by Leibniz in 1692, hundreds of years ago. And so it's viable now. So the stable bipolar magnets, microscale, nanoscale magnets as a digital data storage in hard disk drive, that has been my work, and to invent launch the perpendicular drive to the market. And those systems, digital systems, allow data to be stored and duplicated and transmitted and processed in computers. Those are very convenient systems thanks to digital data. So thanks to it, so the tons of data is being exploded, and the upper half is the world's total data creation is presented by David Rinzel, IDC. And 11 years ago was only a 1.2 zettabyte. In the last year, the 44 zettabyte. And 4 years from now, 2025, 175 zettabyte of data will be created by human being. So it's a big data. Even for quantum computing, the big data creates the optimized problem to be solved in quantum computing. So big data is a must for everywhere. Tightly coupled data and high performance computing and quantum computing will be required in the near future. So this is the smart city network I'm working on in the northern part of Japan. It seems like brain. I would say it's brain-like data connected smart cities. So a lot of big platform, including cloud at the center, and a small database is disaggregated area-wide, and at small edge data center close to the citizens. So it's a disaggregated data platform networks from cloud to edges. So importantly, there has to be flexibly configured, and it should be resilient against disaster or power down. So 24/7 infrastructure monitoring and industrial supply chain management and real-time energy supply control. And in the near future, the autonomous driving will use those kind of systems. And for tsunami and a big disaster, real-time guidance for disaster evacuation is very important to save lives of people. So a brain and data store, this is kind of a way of thinking in my research. So I like to redefine data storage. Data storage used to be, data storage has been, it's kind of passive container to store data. But redefine data storage as a computation unified active system, because the data inside the container has much more value than container itself. So the computation analytics has to be unified in the internet to minimize the cost in terms of power and time to analyze it. So I like to do this by learning from brain functions. At the top here, this is the requirement definition by data-heavy application. This will tell us about how the system should be in the future. And the requirement definition will be made and to give us a directional guidance of the data analytics platform and the architecture, how it should be. And so that will hopefully give us a solution for real problem in current computer and data store. So neurostructure analysis is a big example of huge data, heavy data-driven application. And that is the motif of the storage device research currently ongoing. So brain-inspired computing will be bringing the internet. So I.O. structure in a macroscopic view of the brain. So we have 5 senses from eye, ear, nose, mouth, and touch. So the sense inputs. So those go into the brain to make learn from the experienced memory and program scheme to make a decision. But brains are nerve connections, and nerve connections are tons of experiences made by experiences. In other words, made by the data of the experiences, and the brain will give us the reaction, and there's a quick feedback to the sense to stabilize it. So this is the I/O structure of the macro in the macroscopic view of the brain. So entire brain, look at the entire brain. The brains are brain-wide interconnects. The brain has connections. Someone call it it's connectome. And no bipolar bits or no monopolar bits is stored as data, like hard disk drive or flash memories. So all connections, all about connections. This picture is a diffusion tensor imaging of the human brain. It's a short length or long length connections are here. You can see it. And neurons and synapses, those are very microscopic view of the brains. It's a minimum scale view of the brains. So the neurons are connecting to the neighboring neurons with the synaptic terminals. Those are the communication contacts between neurons and axons and transmission lines. In the human brain, we have 86 to 100 billion neurons. And each neuron has 1,000 to 10,000 synapses. So it turns out there's about 150 trillion synapses in the human brain system. It's huge, huge. I cannot imagine that even those systems are in my head, but it's difficult to miss that. So, looking into the very microscopic view of neurons and synapse. So Hebbian theory tells us here, the neuron cell A and the neuron cell B and synapses are closer to the cell B. If neuron cell A and B fire together at the same time, then the synaptic strength is increased. So it's a fire together and the wire together. Then the long-term potentiation, LTP, is made. In other words, it is kind of a learning process. Spike time-dependent synaptic plasticity. That's a microscopic definition of learning. Brain sensing, I like to show how we sense the brain itself. So with the macroscopic view and the microscopic view, I have 2 slides in it. So this is a macro scale functional mapping. We usually use MRI, functional MRI to look at it. It captures the whole brain, how it works, and the parts to parts, and with a resolution of 0.5 millimeter approximately. So the recent functional MRI creates tons of data. So dynamic image can be captured. Only a 20-second session, the data will be is about 300 gigabytes. If we continue the experiments in 1 hour, so that will be 55 terabytes. It's a one single data set. It's huge. But it will tell us how how brains parts are connected to each other or interacting each other. We can see it. If we goes into the very microscopic view of the brain, that is this. Mostly for animal experiments and fluorescent microscope to look at how the neurons are connecting to the neighboring neurons, or how the structure of the neuron spaghetti. Electrodes probing or fluorescent microscope is being being used, and in case of light sheet fluorescent microscope to look into the structure of microscopic structure of the neurons, that will tell us tons of data again. Some system will create, some system can capture even the spike movement. So 1 gigapixel CCD or CMOS image capturing system can take 1,000 frames per sec to capture the move of the spikes, and 10 bits in depth will be 10 terabits per sec. One session will be easily sub-petabyte or even bigger than petabyte. So 1 hour session will be a 4.5 petabyte and even one single data set. That's huge. So let's look at this, the visualization of a whole brain. It's a small brain. This is a small fruit fly flying around the fruit, the banana, the pineapples, and melons. So those are called Drosophila, small brain. It's smaller than sub-millimeter size. That is captured. The image is captured with a expansion microscopy with a laser light sheet microscope by MIT. The images are retrieved from the disaggregated data store using the 3D visualization tool and the computer node here. So this is the entire picture in the right and left with two balls. That's a optic lobe of the eyes, and center of those are the center of the brain. The enlarged image here, like a Google Earth, getting into the deep into this brain structure, and we can see neurons here. It's colored. I'd like to show you the video. So another file. Let's see this. Okay, this is a video. I can see flying into the brain of Drosophila, getting into the center of the brain, and you see neurons and connections, tons of connections, even for a small fruit fly. Going back outside, and you see two optic lobes, right and left, and getting flying into it again. So we are flying into the depths of the brain. We are showing just 1% of the neurons, just for a visual. So the real neurons are 100 times denser than this. So even a small fruit fly. Okay. Let's go back to here. This is Drosophila whole brain neurons. So likewise, Google Earth, we need to look at the entire whole brain into a small single neurons. And it's a multi-scale, very big scope. So multi-scale 3D analytics of brain structure. This is an example of the mouse hippocampus neuron structure. So synaptic contact, it's a nanometer range. So 10 to minus 9 meter. And the whole brain is a centimeter range or 10 centimeter range in a human being. So it's a very big order. But using this order to capture the whole whole view of the how brains are working in terms of structure, in terms of the communication, the variety of aspects. So basal ganglia is an interesting module in the compute in the brain. So cortical basal ganglia loop, this is the key loop of the brain for us, is from the cerebral cortex or basal ganglia and thalamus, and make a loop here. And this is connected to the hippocampus for episodic memory and amygdala, emotional memory. This is a simple module of the program here. It's a compute in the brain. So the simple program computes the function is section of intended motor and ignite the motor. Okay, look at this. It's a parallel cortical basal ganglia network of the human being. Simple program, only one or two, a small number of program for fish, a small creature, and a sophisticated program like a human or monkeys. So those parts are separated, but still use the same simple program. It's a parallel processes for various information and actions. And those are interactively moving. So sophisticated, very sophisticated program. So those have some assignments. This green in color is prefrontal loop. They are doing planning, memory, and warning, providing warning. And the oranges here is oculomotor loop. controls the eyes movement and the visionary control. And red here is the motor loop, is a motion control. And the limbic loop is emotional and motivation control. Yeah. So those are the one of the functional part of the brains, and those are also connected into hippocampus and amygdala. And this is a sophisticated program, and it's between macroscopic and microscopic. It's a mesoscopic view of the brain, and this part is very interesting to see the real computation. So modularized computing brain and cortico-basal ganglia loop in the last slides. So long-term and short memory embedded, and information path direction is being done. And the winning connections are the key feature of those. So there is no digital bit stored. So they are with connections. Let's look back to the current computing system. It's a data tier. The vertical axis is a computing tier, top as a processor at the top, and cache, DRAM, storage devices down to archive. And the horizontal axis is a latency, how fast we can access those information. So processors are fast, but mostly the volatile devices. And the storage device is a big capacity, the huge capacity to store data, but and non-volatile, but they are very slow. But we have to move data back and forth to do computation or analytics. For better understanding, I make this latency kitchen model. Okay, I'm a cook. I'm cooking in a kitchen, and I am a CPU or GPU. Okay, and convert the latency to a light travel distance. How far we can go in some given latency. The processor running at 3 gigabits per sec is just 3 centimeters of the light travel distance. And L1 cache to L3 cache is a 30 centimeter or 3 meter in the kitchen table, on the kitchen table. It's easy. The DRAM is a 10 meter away, but still in the kitchen room. But solid-state drive, flash-based solid-state drive is very fast, but 3 kilometers away. It's a supermarket in town. And hard disk drive, it's a 2,000 kilometers away. It's a country next to you, or more farther than that. So, but we are moving who's back and forth for cooking. So that's a real system. So, in order to solve those problems in time cost and power cost, so we made the modularized computational storage devices. As a key value data allocation and tiered memory stack with the fast access to the data. So this box is on one module, including computer node, and underneath it, tiered memory stack with the DRAM, STM RAM, and SSD to make a short latency access through the tier down to the value store, which is hard drive. So those are the system to work for the quick access to analyze the data without moving the huge data throughout the network. And key search in the STM RAM and the metadata or key LBA conversion and solid state drive. And for sequential write, the cache will be on the DRAM or the STM RAM. For reading, NVMe SSD, fast SSD will be will work as read cache. So those are the many system with the conventional devices to make a module. It's a scalable module. In those box, we have a longer term or short-term memory. So DRAM, the short-term memory, hard disk drive, the long-term memory. The information path direction depending on the kinds of data, and the winning connection is programmed. So this is a disaggregated parallel module network. I would say cortico-basal ganglia network-like system let's look at this picture. Two drives are one set of modules here, and 72 sets of the sets of modules make the cluster in a box. So the system will bring the 100 times, 100x or more faster than the single drive. It's very fast. So this is the 3D visualization system. We're now on the way, on the process, in the process of building those stuff. It's a neural structure analysis system inspired with the brain function. So we analyze the brain itself, but the system is learned from the brain itself. It's interesting. The background is the optic lobe Drosophila, behind the eyeball, inside of the eyeball. Those are pictures like this. And the specimen is cut into the small pieces, very small pieces, and the parallel microscope scanning, microscope sequencing create the big data, 10 gigabit per sec. And those are sucked into the computational storage device here. I would say this is a micro scale arrangement. What they are doing is this, stitching the nearest piece of the data. This axon should be this axon in the next piece. So it's a stitching and also registration of each pieces of the specimen. It needs some calculation or computation to make it, to identify what is the single neurons throughout the brain. This is stitching work here. And to bring those data into the here, the disaggregated computational cluster system to make an entire brain picture like a Google Earth, rendering and the nerve tracking throughout the brain. And this is macro scale arrangement of the brain. But we use the same module here, like cortico-basal ganglia loop. So we just same scalable system to make the entire analytics system here. Okay, this is the multi-scale structure as a system. I map the pictures I used in previous slides. From the left, macro scale; at the middle, the mesoscale; at the right, the macro scale here. And the brain side, the macro scale, the node will be a cortical region here, and the edge will be a white matter pathway. And the mesoscale here, so the node will be a cortical column down into the edge. It's a cortico-basal ganglia loop here. This is the edge. And down there, down here, in the macroscopic view, the neuronal soma is a node in synapses at the edge to make a connection. In the computer system, the macroscopic view here, the nodes are clouds, and that is connected to the edge. It's a local data center or a town data center here to capture the local data. And a mesoscale, the disaggregated cluster, this is the node and getting into the small edge here, the computational storage module. And each module is called that at the edge. It's called edge. The microscopic scale here. And then also neural network, multi-layered neural network. And getting into the edge, it's a single device, a spintronics device, MRAM type of spintronics device. So those are the big picture of the multi-scale structure as a system. So when we build a big system with brain-morphic or brain-inspired computing, would like to position each technology into it to make an entire working system. So let me summarize it. So we should recognize the whole brain as a system, not parts, not part. So brain has multi-scale functions from synaptic contacts. It's a nanoscale synaptic contacts to a brain-wide associated memory and communications. It's a huge order difference. So parallel processing in the cortico-basal ganglia loop module structure. This is very interesting structure. It's one of the good references for future computational scheme. I would say the future brain-inspired computational scheme. The modularized computational storage is scalable and applicable to big data set analytics. So this is similar, but this is not identical to the brain itself, but we have a lot to learn from brain itself. I'm very excited to learn from the brain. Thank you very much. Thank you.
Thank you very much for the excellent talk. We have 10 minutes for the Q&A for the audience. If you have questions, you can unmute yourself and ask questions. Maybe I can ask some questions first. Prof, my understanding that you are involving with building the smart cities in the Japan, and you also mentioned about autonomous driving in Japan. I'm always curious, okay, because this driving involves safety. I'm always curious, let's talk about Japan. In your opinion, when would Japan start implementing this autonomous driving?
For a small test bed of autonomous driving, it's already there in a small town. I would say it's a closed town.
Yeah.
It's capable for people to manage this, and and also, I think you remember it in the Tokyo Olympic Games. There were autonomous driving bus system was operated in village for athletes.
I see. And then,
so it's still in a closed place.
Yeah, and then, let's say roughly in how many years would the whole city or the whole country adapt into this autonomous driving scheme?
The whole country, including.
In your opinion,
I would say maybe 10 to 15 years.
Okay.
And Tokyo is very crowded in a kind of unique city. But other than Tokyo, there are many country area. So it's kind of easier for people to use autonomous driving. It's less crowded.
I see.
Yeah.
So 10 to 15 years.
Yeah. So how about Singapore?
I think it will be easier because the country is smaller and it's easier to control, in my opinion.
Yeah, and Singapore is more controllable, look like.
But I'm not sure how much time would the Singaporeans would adapt the concept, because they may think it's not very safe or.
Yeah, for the people or citizens, always get what is take. So that's kind of political things. Eh?
Yeah.
Yep.
Okay. If no question, can I ask one more question?
Sure, please.
Yes. I have seen a lot of beautiful pictures in your slides, and you talked about the structure of the fruit flies, also the human brains. From my perspective, let's talk about only the hardware. They are similar. I mean, talking about there's just a neuron and connections.
And neurons is a connection. Everybody knows neuron is waiting connections. So at the hardware point of view, I think with the current devices, we can make the same functioning device.
Yeah. So that's what I'm talking about. So the building blocks looks like similar.
Right.
Then the major difference for my preliminary understanding is only mainly because of the size, right? The human brain is way, way, way bigger than a fly brains. Then my question,
150 trillions of synapse.
Then my question is, at what stage or at what scale the creativity, self-awareness, or intelligence, or the real intelligence comes into the picture? Because if we look at flies, we think there's no intelligence in flies. They just do some basic reactions. There's no self-awareness, there's no creativity, inspiration, there's no intelligence. So at what scale or whatever, or there's some special thing happens that creates these things?
Yeah, I mean, this is meant on the definition of intelligence. In terms of flying capability, fruit fly has much better intelligence than us.
Oh, okay.
Right. So they are very much customized.
Okay.
So the neurons of a cluster of neurons, a cluster of this basic ganglia loop type of things, are very much easy to be customized for creatures and animals. So that's a very important point. It's in the slides I said scalable, but it has to be scalable and customized in terms of functions. That's a very important point of the the structure of building blocks. But I still have I don't have enough idea to show the entire structure of this, but I'm still working on this.
I see. Okay. And probably I have time for more questions if no audience asks questions. Okay. So you are dealing with data storage. And in the beginning of your talk, you mentioned about the scale of the data is getting bigger and bigger. It's almost exploding. And at a certain stage, in my naive understanding, the data will be so huge that people not able to find the useful information because this is just too huge. I mean, let's talk about probably 50 years later because the information is so huge. Then should we try to either categorize this importance of the memory and also improve whatever searching abilities or intelligence? Because I see the scale is what goes so huge that no one be able to find the important information. It's like
I think you're right. Let's say 100 zettabyte, or I'd say, okay, let's look at 44 zettabyte in 2020. Look back 5 years, how much capacity we have shipped in the market in the last 5 years, just 5 petabyte, 5 zettabyte.
I see. Okay.
Just 5. But the people create 44 zettabyte, which means, so we use just a part of it, or we pick up just the value out of the information, out of data. That's information. So
I see.
It's a condensed value.
I see.
We're filtered.
I see.
The data. So that will be continuing in the future too.
I see.
That's why the power effective and process effective system is required, like a brain.
I see.
Right. And tons of data will not help. So we need valuable information out of it. So that's my message.
So here's interesting following questions, in my opinion. So basically, now we human are filtering the information. So we filter the unimportant information, useless information. We just throw away. But you talked about in future, the intelligence will help us to filter the information or the storage data. But that means we human are giving away our powers to machines. And I'm not talking about that we will have it, but what if that we are not able to control what we learn or how we or what we store?
Yeah, so that is the edge computing, very close to the data source. Where the data is created, the capture data when it was born, and minimize the size to maximize the value out of it.
Yeah, but that may not be okay. The system or the memory is not maximized by human anymore. It's maximized by machine. Then let's say talk about 1,000 years later, human society is kind of controlled by the machine, not by human anymore. So what's your thoughts about these things?
It's very interesting questions. I would say we say AI, right? Artificial intelligence. When A is gone.
Okay.
Yeah. So we are looking at the brain itself and structural analysis or functional analysis. The brain has beautiful power in it.
I see.
But still, we are far from the brain itself.
Okay.
Just the beginning of touching brains.
I see.
I cannot say more than that, but interesting.
Yeah. Okay, great. It's a perfect timing. I think, yes. Thank you very much for the excellent talk and all your excellent answers.
Thank you. Great conversation. Thank you very much.
Thank you. Now we can move on to the next speaker. Next speaker is Prof. Nomura. Prof. Nomura is from, yes. So can you share your screen? We can see your screen, but not the slides.
Just a moment, please.
No problem.
Yeah, can you see my slide?
Yes, it's come up a little bit slower. I hope the connection will be great. Okay, so the speaker is Prof. Noroma, and he will talk about reservoir computing with patterned nanomagnets. Please enjoy the stage. Thank you.
Thank you for your introduction, and I'd like to thank the organizer to invite me to this conference, and we are really happy to share our research. And today I'd like to talk about reservoir computing, and this is a kind of, I think this is a kind of edge computing. So this structure can filter the data and enhance the value, I think. So today, this is an outline of my talk, and I'd like to start from introduction. And here I'd like to talk about reservoir computing, and our reservoir is based on magnetic quantum dot cellular automaton, which is a kind of intelligence memory in logic. So I'd like to introduce the reservoir and MQCA, and after that, I'd like to talk about artificial spin space reservoir and magnetic nanowire reservoir, and I'd like to conclude my talk. So this is my introduction, and everyone knows that these days a neural network shows a very excellent performance, so they can play game of Go, and even they can do art. So this figure is really good. I can't draw like this picture, and the neural network can also recognize a sentence and create a really photorealistic picture like this. So this is a virtual bird from this sentence. And these neural network are created by a brain-inspired technique and run on the computer. And these days, we want to increase the performance of the neural network and do automation driving or lots of things. And easy way to increase the performance of the neural network is just increase the number of the neuron in number of the node in neural network. And previous presentation, Professor Tanaka shows a really beautiful picture of fly's brain. And the C. elegans have a very small brain, so they can do a very little thing, just eat and sleep. But the fly can fly and go to somewhere and eat something. And of course, the monkey can do a lot of things. So increasing the size of the brain, we can do a lot of things. And we want to do such thing in our neural network. And to do so, just increasing the computer power is a easy way. So from Pentium 4, we have 2 core, and Core i7 is increased. And these days, when we use NVIDIA CUDA, then we can use 5,000 core in just a single board. But unfortunately, if we use such massive size of chip, then the power consumption becomes really large. So this is a little bit old data, but AlphaGo Fun use 176 GPU and it's use 40 kilowatt. So it's very hot. So we want to decrease energy consumption and increase the performance of the neural network. And one way to do is using the application-specific hardware. And all days, everyone use CPU and GPU to perform neural network, but these days, they use TPU, which is a tensor processing unit. It's a special unit for calculating the deep learning. And by using this TPU, they use power consumption from 40 kilowatt to 1 kilowatt, and even the performance becomes better. So this is a nice example for using application-specific hardware. And of course, we can design a more special hardware by using field programmable gate array. It's easy to program the digital circuit and create a specific hardware. And we can do more by using a physical phenomena. So if we can use a physical phenomena as a neural network, then we can ignore the power. We can almost ignore the power consumption of the circuit. And we can create a very large circuit like our brain, I hope. So these days, lots of reserve computing, physical reserve computing is reported, and these are the site references. And today, I'd like to focus on this reserve computing. So I'd like to explain what is a reserve computing. The concept of the reserve computing is introduced in 2001 from Professor Jaeger. And this is a schematic illustration of general neural network and reserve computing. The difference is the general neural network have a small number of nodes and tunable internode coupling. But in the reserve, they can't tune the internode coupling, but they have lots of nodes. And in general neural network, we to get a useful result, we have to train the internode coupling weight and output matrix. So we usually use a backpropagation technique and train these weight and create something. But unfortunately, when we try to use a physical phenomena as a node and internode coupling, then it becomes difficult to train the internode coupling, because the case of, when we consider the case of electrical charge, then there is a repulsive force between the electrical charge, but the strength of the repulsive force is defined at the design stage. So when we fix the size of the capacitor and the distance, then it's fixed. So we can't train it. But in the reserve, we don't have to train the internode coupling. And in this reserve computing, we have to create lots of node and lots of internode connection. And when we prepare a random internode connection, then maybe somewhere the internode coupling shows a trained, similar to the trained results like this. So here is almost same as a trained result. So just picking here, then the reservoir shows almost same as a general neural network. And of course, we have to increase the number of the node, but if we use a node if we use a physical phenomena to the node, then we don't have to care about the power consumption, and maybe we can create a very nice neural network. So this is a concept of reservoir computing. And now we try to create this reservoir by using a nanomagnet. So everyone knows magnet can interact through the dipole coupling. So if you place a 2 nanomagnet, then there will be a repulsive force or interactive force. So if you place a lots of nanomagnet, then these nanomagnets are automatically coupled through the stray field and talk each other. So maybe they can do something. And of course, the magnet can store the data, the magnetic random access memory or hard disk drive. They can store the data for 10 years. So it's very good for storage, but if we can use a stray field coupling, then not only the storage, but they can do a logic operation. So we think this nanomagnet is a very good candidate for creating a reservoir computer. And also the nanowire can store the data. And in the nanowire, the data is separated by the domain wall. So through this exchange interaction, maybe the node coupled each other. So today, I'd like to talk about the nanomagnet-based reservoir and nanowire-based reservoir. But before that, I'd like to explain the magnetic quantum dot cellular automaton, which is really old but basic concept of this nanomagnet reservoir. So this slide shows a schematic illustration of MQCA, which is invented by Professor Calvan in 2000. So it's already 2 decades ago, but it can store the information by using the magnetic direction, and it's similar to the MLAM, but it can also perform a logic operation by using a stray field. So from here, I'd like to explain this MQCA. So this is a kind of intelligence memory. So if we use MQCA, then we can put everything in the kitchen. So we don't have to fetch the food to supermarket. We don't have to go to supermarket. So I try to explain the concept of MQCA. It's kind of MRAM, and it stores the binary data of 0 and 1 as a direction of the magnetization. So this example shows an in-plane version, and we define the elliptical nanomagnets. So the magnetization prefer to point right or left. So it's very binary. So we can assign 1 and 0 like this direction. And in usual MLAM, we hate the disturbance. So we want to cut the stray field from the other surrounding nanomagnet, But in MQCA, we use this stray field. So if you place a nanomagnet like this, then these nanomagnets are coupled each other like a ferromagnetic. So this structure can be used as wire. So information is through to here to here or here to here. And when you place like this cartoon, then the stray field is going around and coupled each other like anti-ferromagnetic coupling. So if you set the binary state of lower magnet as 0, then the top one becomes 1. So this can be used as a NOT gate. And in the case when we place a 4 nanomagnet like this, then this structure can be worked as a majority logic gate. And here we consider these gray dots are input and red dot is output. And we fix input value to 0. Everything is 0. Then the stray field from left-hand side points left-hand side, but top and bottom nanomagnet shows a right-hand side stray field. So the majority direction is light. So the output magnetization prefer to point light. And this is a majority gate. And this is a simulation result. We fix the input nanomagnet and calculate the stable direction of the output magnet. Then we get these results. And this is a truth table. And from this truth table, this gate can be worked as NOR or NAND programmable logic gate. So NOR and NAND is functionally completed. So we can create every digital function by using this gate. And also this is programmable. So we believe this is very useful. And to perform the logic operation, if the shape anisotropy is too strong, then just inputs data is not enough, but we have to do something. And usually we apply external magnetic field to this gate. Then the output magnetization is flip to the lower energy state. So the operation is completed. So this is external magnetic field is called as clock field. And I'd like to show experimental results. And this is a SEM image of our gate. And this is a MFM image. And the single dot is shown as a black and white pair like this. And please focus on the left-hand side. When the left-hand side shows black, then it means the binary state is 0. And white, then it shows 1. And when we set the binary state like this, everything is 0 by using a magnetic force microscope manipulation method and apply external magnetic field. Then the output flip like this and shows good operational result. And this is a different initial state, and it's also good results. And by using this MQCA, we can store the information and we can also calculate the logic. But unfortunately, this is a kind of majority gate. So this MQCA is not good to calculate the nonlinear operation like an exclusive OR. To perform an exclusive OR, we need more than 2 gates to perform the exclusive OR. So in this time, we focus to the reservoir computing. In MQCA, this is a majority logic gate, and it can only do a linear operation, and the information is stored as binary. But our brain stores information in analog value. So, of course, when we use analog value of the magnetization direction, then maybe the nonlinear operation result could be hidden in the small tilt angle of the magnetization. So if we apply the reservoir technique to our MQCA, then maybe we get a better, maybe we can create a better circuit. And of course, MQCA can interact our physical space by using a strain or a microwave or something. So this is a really good sensor, and sensor can store the information and calculate. Then maybe we get a very nice edge device to filter the variable information. So I'd like to move to the reservoir computing. And to explain the reservoir computing, I'd like to use this schematic illustration. So the reservoir computing is one of the supervised techniques. So we need a teacher function. So here's the input, and the input is goes through the teacher function, and this is teacher data. We get a teacher data, and also the input data is stored to the node. And the node, in this case, this is a nanomagnet, and nanomagnet do something and calculate. And of course, to update the magnetization of the node, we have to apply external magnetic field, but after that, the node state is updated and measures the node state and do training. Then we can perform a physical reservoir by using nanomagnet. Okay, and here we focus on the spin ice structure. As you know, the spin ice is kind of, how can I say? Spin ice is very good for computation because the spin ice have lots of magnetic configuration in the same energy. So if you place lots of nanomagnet in a honeycomb structure like this, then this structure follows 2-in or 2-in, 1-out rule, or 1-in, 2-out rule. This is the ICE rule. And the structure shows this magnetization. This is one of low energy state. And these two are a very low energy state, but the lower right-hand side circle shows a little bit high energy state. And this can rotate. So even we focus on the same energy, but the spin ice structure can show a lots of spin configuration. So this means the spin ice can represent a lots of things. So we think the spin ice is really good for computation. And we try to do reservoir computing using spin ice structure. And this is our spin ice reservoir. So there are 72 nanomagnet, and the ring is 19 rings, and each nanomagnet are coupled each other through dipole coupling. And the size, we assume the nanomagnet are composed of permalloy, so we set MS of like this, and the size like this. So thickness is 20 nanometer, and the size is almost 100 nanometer length. And we use X component of the magnetization of each nanomagnet as a node state. And here we use analog value. So when the magnetization is counted slightly, then the X component becomes a little bit small. And we use node state as like this, and we have 72 nanomagnets. So the number of the node in this case is 72. And I'd like to explain how to input the data. Here we assume the binary information for input data, so 0 and 1. And if the input is 0, then we set these 6-dot magnetization like this. So the magnetization is rotating counterclockwise in case of 0. On the other hand, in the case of 1, the magnetization rotates clockwise like this. So this is a snapshot after the input data is written to these nanomagnets. And after we load the input data, we have to update the magnetization. So we apply external magnetic field. And here we apply external magnetic field in this direction and this direction. So we input 6 times, 6 external magnetic field in this direction and updates the state. Why we use 6 is we have 3 direction of the nanomagnet here, and here is a parallel, here and here is parallel, and here is parallel. So we have a 3 set of angle, and from this easy axis, we apply external magnetic field from 20 degrees from each nanomagnet easy axis to a plus and minus direction. So we can update everything like this. And after updates node state, we measure the node state by just picking the X component of the nanomagnet, and we use to output signal for output signal. And simulation is done by using LLZ equation. It's a really general method, and we just assume that the magnetization have a single domain state. So nanomagnet have only single magnetic moment. And we just use a Runge-Kutta method. So it's really general method, and we calculate the node state. And to check the performance of our reservoir, we use a STM task and PC task. This is a very general task. And in STM task, we just set the delay. And when we hear and delay is 1, 2, 3, then the teacher function becomes 1 again. So STM just shows the memory capacity. But in the PC case, we also set the delay, but in the PC, we sum up everything and we do a modular operation by using 2. So this PC task shows the capacity of memory and nonlinear operation. So this PC task is really difficult compared to the STM task. And okay, and now we have node state. This is just the X component of the magnetization. And we have a teacher function of PC task and STM task. And by using this teacher function and node state, we train the output matrix. It's just a dot product with node state, and we get output value. And to reduce least mean square error, we train this output matrix. And these are really general method. And this is a variation technique. We calculate the correlation between teacher function and output data and sum up every delay, and we define the capacity. So the capacity becomes like this. With delay of 1, correlation square becomes 1, and 2, in the case of 2, it becomes 0.9, then here 2 shows 1.9, and it's sum up, then maybe this becomes 3 or something. So important thing is, if we say STMC is 3, then we can memory 3 things in the reservoir. And PCC is 3, then we can memory 3 things and do a nonlinear operation with this 3 bit. Okay. So, okay, and this is the results. Left-hand side shows STMC capacity, and right-hand shows PCC capacity, so nonlinear operation capacity. And horizontal axis shows aspect ratio of nanomagnet, and vertical axis shows the magnitude of clock field. And if you set optimized aspect ratio and clock field, then we get a PCC and STMC of about 3. So if we use a 72 nanomagnet, then we can measure the 3 things, and we can do a nonlinear operation with 3 things. And by combining this technique to a edge device, we believe we can create a nice filtering device. And maybe I have 4 minutes, so I'd like to explain another reservoir using a nanomagnetic wire. So in this case, we don't use a nanomagnet, but we use a nanowire. And this structure is inspired from domain wall logic shift register in 2010. This is a domain wall shift register, and by applying the rotating fields, stored data is shifted from left to right. And by creating 2 rows of this shift register, then we get a better performance of with STM task and PCC task. So in this case, we split area like this, and again, we use just the X component of the magnetization as a node state. And if we apply rotating field like this, then the magnetization is changing like this. And it's a little bit difficult to recognize, but later I'll show the nice shift register results. And when the rotating field becomes here or here, we create a domain wall in the input area. In the case of input 0, we create a domain wall right here when the external magnetic field is 130 degrees. And in the case of 1, we create a domain wall at external magnetic field of 310 degrees. And okay, this is the results. And here we define the least, we use a least significant digit. So we launch the data with some digit. So LSD is 10 to the minus 1, then 0.673 becomes 0.7. So it's rounded. So in experiment, we can't use lots of digit, but we have to average it. So we do such things. And even we only use 4-bit or 3-bit, STM really shows good performance, but PC, in the case of PC, even we use a 3-digit, digit is here. Even we use 3-digit, but the PCC becomes very nice value of 5. So when we use a domain wall logic, also we can create a nice reasonable computer. And I'd like to show a weight matrix. So weight matrix means which node is important to calculate the actual task. And this is a case of STM with a different delay. Here is delay 1, here is delay 2. And with increasing of the delay, the important part is shifted from left to right. So it's really a shift register. So when we consider just a shift register, it's a very linear task. So we don't care the very small change of the magnetization. But in the parity check task, it's non-linear task. So not the large domain area, but the domain wall becomes very important. In the case of delay 1, maybe we can calculate from domain, but in the case of delay 2, the important part becomes only the domain wall position. So at the domain wall, they can calculate a non-linear operation. And with this, so important thing is we can, when we use an analog value of the patterned nanomagnet, then we can do a linear not only the linear operation, but we can also do a non-linear operation. So moving to the binary state to analog is really good for our nanomagnet computing. And it's already, time is over, so I'd like to conclude my talk. We introduced artificial spin-ice-based laser and nanowire-based laser. And in the case of artificial spin-ice laser, we get STMC and PCC of 3. And in the case of nanowire version, we get both of 5. So it's really good for the laser, I think. And I'd like to thanks to this grant, and also I'd like to thanks to your kind attention. Thank you very much.
Okay. Thank you very much for the excellent talk. And now our session is open to Q&A. If we have enough time, we will have 8 minutes. Okay, 2 participants raised hands.
Dr. Rajib.
Yeah, Professor Rajib.
Thank you very much for the nice talk. I have a question regarding this artificial spin-ice system consisting of nanomagnet that you were discussing about. So the magnetization states were changed using the external field.
Yeah.
Which might be quite resource intensive in the sense that, I mean, you need a system to apply this magnetic field. Wouldn't it be easier to use something like a spin transfer torque, like electrical current based, driven based switching system, or maybe even the something like multiferrics where you can use the strain to manipulate this? Are there studies that have been done using those kind of systems as well?
My answer is now we're working on to use such thing, and actually we want to control this structure using voltage, VCM effect. So
okay, so it's the same thing, right? The multiferrite. Okay, so strain control.
Yeah.
All right. All right.
If possible, then it's really become a good structure. So in actual device, the external magnetic field is not very bad, I think.
Yeah, it's not bad. I mean, I was just asking maybe some more active methods rather than, I mean, magnetic field is also an active method, but the electrical control will be a much better industrial option. Yeah.
Yeah, but it's difficult in our lab.
So in that case, if you are thinking of using this multiferrite electrical field control switching, where the ferroelectric and ferromagnetic need to be coupled, it will be difficult to use the ellipsoidal system like what you are showing, because they have a very large uniaxial anisotropy, and then the easy axis is very difficult to move around.
Yeah.
So you will have to go for some other special nanomagnet shapes, like what has been proposed, like peanut shape nanomagnets or something like that.
Yes, and
just a comment.
yeah. Thank you very much.
Okay, great. I think Ramu also raised his hand, so you can unmute yourself and ask the question.
Yeah, thanks, Nomura Professor, for the nice talk. So I have a question for computing reservoir in nanowires, where we are considering nanowires, different nanowire structures which are actually parallel to each other. So in terms of the magnetostatic interaction considerations, so one domain will affect the other domain in the other nanowire. So how much probability of getting the possible output?
Sorry, I can't get you.
I mean, within this figure, as you can see here, there are parallel wires, right?
Yeah, parallel wires.
So
yes.
they can talk each other in the sense like the magnetostatic interaction between the wires can affect one wall to the other wall, right?
I think no. The magnetostatic interaction between the wire is very small compared to the exchange interaction. So in the origin of the PCC is, we think it's from the shape of the domain wall. So it's from the exchange interaction. And we have two wires, so there are delay, half-bit delay at here and here. So maybe that delay is important for a PC task, I think.
What is the spacing between these two structures?
It's not small, just a moment, please. Here is 200 nanometer wide nanowire, so yeah, 200 nanometer.
Okay. Yeah. Thank you.
Thank you.
Do we have more questions? Maybe I can ask one question. I think if we generally, my understanding is if we want to get the output, we typically convert the signal to either current or voltage in order to commute, right? And so in the system that you proposed, how do we, let's see, read out the output? Do we measure the resistance of the channel, or we have some special technique?
Actually, this domain wall structure is very difficult to read because electrical current can flow along the wire. And in the case of spin-ion structure, we think we can use MTJ to read the magnetization. And now we're working on to create an MTJ structure with ICE in Japan.
I see. But if we talk about reading the structure using MTG, that means, my understanding is that means for every nanodot we need MTG.
Yes, and actually no, and in this case we only use least mean square method to train the matrix, so we need everything. But recently we apply lasso, so we can ignore some nanomagnet and we can just read the important one. So we can reduce the number of the IO I think.
Okay, so that would make the fabrication much easier or
Yeah,
affordable.
yeah.
I see. Okay. Looks like no other questions. And it's almost perfect time. So I think it's almost perfect time to end the session. And thank you, everyone. Thank you, every speakers of the session. And thanks. Prem, now I hand over the mic to you. Probably you want to remind everyone to come back this afternoon.
Thank you, everyone, for attending this session. We'll again resume our session at 3 p.m. Singapore time, which is 4 p.m. Japan time. So in about 4 hours, we'll meet again. See you. Professor Tanaka, do you have anything to say?
Not special. Okay, see you in the afternoon.
Okay, thank you all. Bye-bye.
Thank you.